No, I think it's always good to check that. Yeah. Um, and so, if you check those, if you check those reaction forces and you check, and you should get something similar then to, what you would get from a free body diagram. And so, yeah, absolutely. I think that's a great way to check simulation results. Mhm. So you're talking in terms of like simplified models or validations or things like that? Hmm. Yeah, no, I think that's a great way to check. Yeah. All right, it's 4 o'clock, so let's go ahead and get started. All right, good afternoon, everyone. How's everyone doing today?
Good. Thank you, Professor.
Good,
Doing well.
good, good. Yeah, I know it's we're almost at the end, so I'm sure everyone is tired at this point. Oh, got your second dose, so you might be feeling not so good pretty soon. If you're not getting sores and aches already, then you might feel it pretty soon. So, yeah, one of my friends just got it just yesterday too, and she's feeling it today. That's for sure. Okay, and so today we're doing Ansys Activity 6, and so we're taking a little bit break from the thermal simulation that we're talking about Tuesday, but today we're going to be learning about how to do topology optimization. Okay, and so here's just a little bit of a preview of where we're going to go. Basically, the idea with this feature within Ansys is that it'll help you optimize your geometry, right? And so one of the beautiful things about Ansys and just finite element software in general is that you can do all these things virtually, and it allows you to kind of explore things and do things that are much harder to do in person, right? And so one of these things, that's Ansys is useful for is to optimize, your geometry in terms of how much material was used, right? Because a lot of times, when you make a part, you might make a wall bracket that looks like this. You might just design it just through ease of manufacturing. So something like this just might be easy to make. But in reality, for depending on what the application is, and how it's going to be loaded, you probably don't need all this material in order to accomplish your task. And so what would be nice is if let's say that we use Ansys to see, depending on how this thing is loaded, are there any parts, or are there any ways that we can shave off the geometry to save some material but still accomplish the same task, right? And so that's what we're going to be looking at today. And so this feature in Ansys is called Topology Optimization. Let us do just that. Okay. All right. And so just like I mentioned earlier this week within the email, so this activity is going to be optional, and so it's you can turn it in, and you'll get a minor amount of extra credit points for the homework, but it's not anything too major. And so I know you guys have a lot of stuff going on right now, and so if you don't have time for this, then it's no worry. But if you do complete it, I do want to reward you a little bit for it. Okay. And so the due date for this is going to be next Friday, May 14th at 11:59. But again, totally optional. Okay. All right. And so another announcement I have to make is that I've been talking with one of our Ansys reps here at Cal State Fullerton, and I'm trying to arrange for a guest lecture next Thursday, right? because everything, everything I've been teaching you in this class about Ansys, it's coming from my own perspective with very little knowledge of industry. And so, I've talked to people in industry and about how they use Ansys, and I've tried to design this class as best as I can to kind of prepare you for that. But, it's never quite the same thing as having someone in industry come and talk to you about, how they use Ansys and what's good. And so, I'm trying to arrange for next Thursday to have someone from industry come in and talk to you guys about that. The details, I'm still kind of working out the details. So it's looking good. So it's looking positive. I don't know who it's going to be. And so right now it's kind of being arranged by the school. But I've expressed strong interest. I know you guys would have strong interest in that as well. And so I'm trying to get that done. And so, if we do that, it'll be next Thursday, May 13th. And I'll send it and once all the details are set, I'll send an announcement for that as well. And so I think that'll be kind of a nice way to end the class, because I think my goal for this class is for you guys to leave and to be able to use Ansys in industry, right? And so we've been going over all kind of the basic skills, the basic features in Ansys. But I think to be able to hear from someone who uses Ansys professionally on a daily basis, I think that would be something that it'd be kind of like a nice bow tie on top of this class. Right?
Question.
Yep. Mm-hmm.
So as for assignment 6, so if we do assignment 5, would assignment 6 count as our missing homework, I guess you could say?
So if you don't do assignment 6, then it'll drop. Canvas will drop a different homework, your other lowest homework. But Ansys activity 6 is only worth 1/5 of the points of Ansys activity 5, and so Ansys activity 5 definitely worth more points. And so and in the grand scheme of things, activity 5 I think is more important for kind of general Ansys skills. And so I would get that one done for sure.
Okay.
And I am going to push the due date back for Ansys activity 5. So
Okay,
since activity 6 is going to be optional now, I'm going to push the due date back for activity 5 until Tuesday. And so I think originally it was due tomorrow at 11:59, but I'm going to push that back to Tuesday to give you guys a few more days to do that.
That helps a lot. Thank you.
Yeah. Mm-hmm. Progress report. So the progress report, that's still going to be due tomorrow at 11:59. And for the progress report, it's I'm not looking for anything in particular, and so I'm not looking to test a milestone. It's more of like a completion, kind of a check-in, right? And it's partially there just to kind of help encourage you guys to work on the project. Because what I found is that if I don't put checkpoints, then I think a lot of people kind of put it off until the very last minute to do it. And so I have this progress report just for me to check in, just see how you're doing. And if you haven't really got much done for the project, that's totally fine. You can just turn in a progress report that said this is all that I've done so far, and that's fine too, because I'll be reading all your progress reports probably on Monday. And then based on where you are and based on what you're struggling with at the time, I'll help you kind of work through. I'll give you feedback on some of the issues that you're having, and I'll help you roadmap and say, we only have about 2 more weeks until the project's due. So let's try to get these things done by this time. And I'll help you kind of schedule out kind of a schedule so that you can complete the project on time. Yeah. So for the progress report, just don't stress about it. Just let me know where you are. And the more detail that you give me, the better, of course, then I can give you more feedback on it. But, it's something that I'm just grading for completion, and it's just kind of a way for me to check in where you are and for me to kind of help you out to get you to the finish line. Okay. So any other questions before we get started for today? Okay. All right, so let's go ahead and get started. And so I don't think it'll take us the full time to do this topology optimization. And so whatever time we have left, we'll go ahead and continue on with the thermal stuff that we started on Tuesday. Okay. All right. And so let's talk about topology optimization, right? And so this activity was kind of designed within the same vein as Ansys activity 3. Okay? And so if you remember what that activity was, that was our activity with the signpost, right? And one big part of that project was, I asked you to take the results of your Ansys simulation, and then I asked you to use that to redesign the signpost, right? And so what most of you did was you made the post thicker, right? And so to enable the signpost to handle a larger amount of stress, one way that you could have redesigned that post was to just simply make it bigger, right? But I had you do that manually, right? And so, what I told you was that, if you want to redesign the post, you would have to go into the CAD software and actually make the post and actually make it bigger like that, rerun the simulation, and then go from there, right? And so it would be really nice if Ansys had a tool to kind of help you kind of digitally optimize your geometry, without you having to manually go in and do stuff, right? And thankfully it does, because that's the subject of today's activity, right? And so in today's activity, we're going to use Ansys to shave away unnecessary mass from a part that may not really be doing much for the structure, okay? And the feature that we're going to be using for this is called Topology Optimization, right? Okay, and so let's go ahead and get started with the project. Oh, I was testing something else. No. Okay, and so our starting point, as always, is going to be Ansys Workbench, okay? And then what we're going to start with actually is going to be a static structural simulation. And so I'm going to take static structural, I'm going to pull it up here, okay? And then just like we always do, let's go ahead and load in our geometry. Okay, we go ahead and import the geometry. Right. I haven't had a chance to test this today, but we'll go ahead and see. And so on the on the Canvas site, I've uploaded this CAD geometry for you. And so it's called wall bracket for optimization. Okay. And so I created this geometry within Ansys Design Modeler. And so it should import without any issues. All right, so let's go ahead and import the geometry and go ahead and double click model. And this will open up Ansys Mechanical for us. My computer's been working overtime the last few days, so it might be a little bit slow. Let me go ahead and close MATLAB. There we go. Come on. Can relate to the computer. Yeah. Even the computer is ready for summer break. Okay. And so here is our geometry. Okay. And so it's a simple just wall bracket. Okay. And so you can imagine, for these 4 holes right here, I'm going to basically bolt it to the wall here. And then I'm going to have something attached to the ends down here. Okay. All right. And so just like we usually do, let's go ahead and apply a mesh. Right. And so the only thing I'm going to do here is I'm just going to apply a mesh sizing. So let me go ahead and apply to the whole thing. Okay. And let me apply a mesh sizing of 20 millimeters because that's what's listed in the problem document. Okay. Let's go ahead and generate our mesh. Okay. And you can see from this mesh right here, let's check the number of elements. And so we have about 19,000 elements. And so that's pretty significant actually. So that's a decent amount. Okay. All right, so let's go ahead and add our loads and constraints. And so first thing we have to add here is our fixed supports, right? And so to kind of emulate the fact that this bracket is going to be bolted to the wall, I'm going to go ahead and fix it at all of these locations here. Okay? So all these bolt holes. Okay? Right, so bolt hole there, bolt hole there, bolt hole there. Okay. And so now we're all fixed on those places there. Okay. And so let's go ahead and add a load, right? And so I'm going to add a force load, okay? And so I'm going to add the force load on the holes out here, okay? Okay. And so just so we're emulating the effect of we're hanging something from this bracket. Okay. Let me go ahead and supply this by components, and then let's put the load in the -z direction. And let's apply a load of 10,000 newtons. Okay, right. Right. And so if we look at all our boundary conditions, we have a fixed support on the places where it attaches to the wall, and we have a vertical load of 10,000 newtons that's being evenly distributed between these two holes. Okay. All right. And so let's go ahead and add our results. So we're going to add total deformation field. We're going to add equivalent stress field. Right. And let's go ahead and hit solve, and we'll see how the simulation comes out. All right, and so here is our results. And so here you have the the equivalent stress field, okay? And here we have the deformation field, right? And so, before we move on, let's do just a quick sanity check. And so, we know that we fixed the bracket here on the right-hand side, okay? And so if we check the deformation, we see that all the deformation here is 0. So that makes sense, okay? And so where we have the maximum deformation of about almost 0.5 millimeter is, here at the ends of the bracket, okay? And that makes sense because that's where we're loading it, okay? And so if we look at the equivalent stress field, you can see here that we have a maximum of stress here, kind of near where it attaches, and the maximum stress there is some kind of bending stress, most likely. All right, and so this looks fine, right? And so we've done Ansys static structural simulations a million times now, and so we know what to get from the results, right? All right, and so one thing I want you guys to notice from these results before we move on to the optimization is I want you to look at the locations in this bracket where the stress is very low, right? And so we're looking at areas where the stress is basically dark blue, okay? And so you can see here we have dark blue over here, kind of in this this area in the middle of the two fixed supports, and we have very blue here, in between where the load is. Okay, right. And so what does that mean? And so when a part is under a low amount of stress like that, one way that you can interpret that is, these regions of the bracket are not supporting any of the weight, right? Because this bracket is being weighed down by these holes right here, right? And so the regions where we have high stress, those are the regions that's kind of the ones that are kind of, carrying the weight, right? And so those are bearing the brunt of the load. Okay. And so the regions where there's not much stress, we can say that, these regions aren't really doing much, right? And so, we look at simulation results like this and we say, okay, looks like we have a lot of regions in our model here which aren't really bearing that much stress. Maybe we can optimize it a little bit, and so maybe we can cut out these areas which are not really bearing that much stress, and still have a part that accomplishes its goal. Okay, and so that's exactly what we're going to do in this next part. And so we're going to use the topology optimization tool within Ansys to basically locate these areas which are not really doing much for us, and then automatically cut those out from the model so that we get a much more optimized geometry. All right, so any questions on this so far? Okay. All right, and so that's actually all we have to do here in static structural. And so let's go ahead and close Ansys Mechanical, right? Okay. And so it's going to bring us back to Workbench, right? And so our static structural analysis is complete. And so our boundary conditions and everything and simulation results are good. Okay. And so what we have to do from here is we have to launch another analysis type, okay? And so I think this will be the first time that we're doing this. And then we need to link the results of this static structural to the topology optimization, okay? Because in order for the topology optimization to work, it needs to have knowledge of what the deformation field looks like and what the stress field looks like in order for it to work properly, okay? And so to do that, we have to directly link this topology optimization to these results, okay? All right, and so the way that we're going to do that is we're going to take topology optimization, which is this feature here in the toolbox. We're going to click and drag this, and then drag it right on top of the solution right here. Okay. Right. And so you can see here, once I'm dragging this topology optimization on top of solution, then after I release it, you can see here that we now have a new a new entry here called topology optimization, and a lot of the things are linked, right? And so you can see on the first case, you can see our engineering data is linked, our geometry is linked, our model setup is linked, And our solution results, which is what we got, that's now linked to the setup of our topology optimization. Okay. All right. And so in order to launch this, let's go ahead and double click setup. Okay. And so this is going to open up Ansys Mechanical again, but now Ansys Mechanical is going to be, equipped with the topology optimization tools. Okay. Right. So that was a little bit faster because we just finished launching it. Okay. And you can see now if we look at the left-hand side of the screen, we have a lot more options here for topology optimization. Okay. All right. And so all the mesh and the boundary conditions, all that is done. And so we're kind of in the realm now of like, now that we have a finite element simulation, what can we do with it in order to further our analysis of this part. Okay. All right. And so our first stop under topology optimization will be right here. Okay. And so we need to set the analysis settings. Okay. And here you'll be able to set some settings to control how the optimization is going to go. Okay. Because what's going to happen here is that the topology optimization is going to take the results from your static structural simulation and then use that to try to find a better geometry than what we have here. Okay. Right. And so the first thing that we have to set here is this setting right here in the bottom left called the maximum number of iterations. Okay. All right. And so let me explain what these iterations mean, because if you've never run an optimization tool before, it can be a little bit confusing. Okay. All right. And so I will say that the mathematics behind optimization it's really fascinating and it's really complicated. And so we're not going to get into that stuff, and so we're not going to talk about mathematical optimization and things like that. But what I will explain to you is some kind of general knowledge that you should have about how optimizations work in general, so that you can work with a tool like this and kind of know what you're doing. Okay. All right. And so when someone says that they're solving an optimization problem, they're talking about a slightly different type of problem than what you're probably normally accustomed to. Because normally, what most people are accustomed to is that, you're presented with some kind of mathematical problem or some kind of engineering problem. You work on it a little bit, you plug into some equations, right? You do some math, and you end up with one definitive solution, right? And so, a lot of math problems are like this. Probably most of the problems that you do in your classrooms are like this. You have one solution to one problem, okay? A lot of times, when you're doing optimization, and this is true for design too, there's not just one solution, right? And so there could be a lot of solutions out there, right? And in fact, the language kind of changes a little bit. Instead of talking about, a correct solution or a wrong solution, what you're looking at instead are, there are some solutions that are better than other ones, right? And so you have lots of different ways you can approach a problem. But instead of saying that, one's the best and everything else sucks, what you're saying is, we have some that are good. And so maybe we'll call those S tier. Okay. We have some that are better. And so those are A tier solutions. We have some that are worse than that, B tier, C tier, and so on and so forth. Right. And so now it becomes kind of a much more of a gradient. Okay. And so optimization problems, they try to look at these kinds of problems where there's not really a defined correct solution, but it tries to find the best solution out of a bunch of ones that could work. Okay, right? And so it does this, by looking at certain characteristics of the solution, right? And so it's not looking for, whether something's right or is wrong, but it's looking for certain qualities that make things better than the other ones, right? And so, let me give you an example here, right? And so think about movies, right? And so usually, when someone thinks about movies, they have people have certain preferences for what kinds of movies that they like, right? But it's really hard. It's if you really push someone, they're really hard pressed to say. It's really hard pressed for someone to say this movie is absolutely perfect, right? In lots of different ways, because for everyone, their preferences and how they rate movies is different, right? And so objectively, you can't really say that there's a perfect movie out there, right? And so, I could say that, I like Rush Hour 2, but, someone might say that they might like The Dark Knight, right? And so it's different for everyone, right? But even then, even though there's no absolute perfect movie, everyone knows that, there's certain characteristics that we look for, in order for a good movie, right? And so, and so that's what an optimization looks to do. So it looks for these certain characteristics, right? And so, like, if you're talking about movies, you might say that, I like movies with a lot of action in them, or like I like movies with a lot of comedy, right? And so your own personal optimization algorithm for finding a great movie is to say, how much comedy is in there, how good are the jokes, does this make me laugh, and things like that, right? And so, optimization is looking more for that instead of like, this is perfect comedy or perfect movie. Yeah. Right. All right. So question. So is it computationally demanding is it computationally draining on the computer given the amount of iterations? Yes, it is. And that's why we have to put a hard cap on it. Right. And so because we're not looking for kind of the perfect solution here to the optimization problem, what we're looking for instead is something that's better or not. The way that the computer basically approaches this is that it kind of does like a guess and check, right? And so what the computer is going to do is it's going to guess a solution, right? And so it's going to guess, let's try this geometry instead. And then from there, it's going to check and see, is this geometry better than our last one, depending on the characteristics that we're looking at, right? And if that's true, then, that's great. And then we pick it. But if not, then we reject it. Okay. And each of those separate guess and checks, that counts as one of those iterations, right? And so the more iterations that you do, the more computationally draining it's going to be, because each of those iterations is like, a separate finite element simulation. And so, you have to be a little bit careful here about how many iterations that you pick, right? Because, you can easily set this quantity here to be something insane, like, 99999, right? 99. And so, in that case, the computer will guess and check, as many times as you let it, right? And more than likely, it'll come up with something good, but it's going to be very computationally draining that whole time to be running all of those simulations. Yeah. So yeah, and so that's basically what we're setting here. And so we're basically setting an upper bound of how many different times the computer can try to find a better solution than the one before. All right. Does perfection even exist? That is above my pay grade, and so I'm not a philosophy professor, and so I will not try to comment on that. Yeah. Okay. All right. And so the amount of iterations that you select here it's a balance, and so and so you can increase the number of iterations here to get a better solution, but it's going to be more computationally demanding. Or you can reduce the amount of iterations here, and so you can make this like 100. Okay. And so this will probably finish a lot faster because you're only doing 100 checks, but maybe your solution is not going to be as high as quality as the one before. Yeah. All right. Okay. And so the other quantity that we have to set here is something called convergence accuracy. Okay. Because what can happen a lot of times, and probably what's going to happen here, is that sometimes the optimization algorithm is going and you're guessing new solutions, and it's already so good that your new guesses don't really change that much from before, right? And so in those cases where you've kind of already searched the entire space and there's really nothing left to search, then what we say is that the optimization algorithm has converged. Okay. And so this kind of sets the accuracy for that convergence. And so 0.1% basically means that if we're testing new solutions and they don't vary by more than 0.1%, then we say don't bother searching anymore because it's just going to be a waste of time. Okay. And so leaving this as the default is fine. Right. And the number of iterations we left that as a default too, because 500 is fine for this one. And so, for this activity, you'll see me, keeping a lot of these parameters kind of the same as their defaults. But, I just kind of want to explain to you what they do so that, if you're using this for your own problem, especially if you want to use this for your project, you kind of understand what each of these key parameters do. Okay. Okay. So any questions on this so far? Okay. And so that's the analysis settings. And so, everything else here we'll leave it as the defaults because they should work fine for most cases. Okay. All right. And so now let's talk about the optimization region. Okay. And so, just like I mentioned earlier in this activity, what the optimization algorithm is going to do is it's going to try to cut away or shave away some material that may not be needed for your geometry. Okay. And so, when you're running this optimization, you need to directly specify to Ansys, which regions are okay to shave away material from, and which regions are not okay to shave material. Okay. Because a lot of times, when you're optimizing your geometry, there might be some parts where it's like, there's nothing I can do about this part. I don't want this part to be changed. Maybe it's something that you ordered and it's something that you can't, you don't really have any control over. And so you can exclude those from the optimization. Okay. And so here's a good example, because here, we have all of our whole regions here, right? And so these are where we apply the boundary conditions. Right now, the topology optimization is going to exclude those from the, from the optimization. Okay. And that makes sense, because that's where we apply the boundary conditions. But everywhere else in this model, we can optimize. So that's why it's all blue here. Okay. Right. And so if you want to change, which regions are, are excluded or included, you can do that from here. Okay. And so the design region, which is what you see first here in this bottom left, this is the region where you can actually, where Ansys is actually going to change the geometry. Okay. And so if there's more regions in the model where you want to optimize, or there's less regions, you can optimize, you can change that here. Okay. And the exclusion region, these are the regions where you don't want Ansys to touch and say, we want to leave this part alone, so that we can keep certain things. Okay. And so typically, and so by default, what Ansys will do is that it'll look at your static structural simulation, and it'll see which parts of the model do you have the boundary conditions on. Okay. And so it'll automatically exclude those regions, because you need to be able to still apply your boundary conditions. Okay. But everywhere else where you haven't applied any kind of loads or constraints, those parts will be fair game for the optimization. Okay. And so most of the time that's going to be okay. But if you have a reason to exclude certain other parts of your model, then you can do that too. Okay. All right. And so you can change which part that you exclude here. Okay. Right. So by default, it's just all the boundary conditions. Okay. So any questions on this? Okay. All right. And so next, let's talk about the objective. Okay. And so objective, you can think of the objective as a way for you to tell Ansys, where, what the problem looks like, right? Because optimization is a very kind of broad term, and so you can optimize over many different things. Okay. And so this objective right here, this is your chance to kind of tell Ansys, these are the kind of characteristics, and this is the kind of things we want to look for. Okay. And so in other words, this is where you tell Ansys, this is what defines a good movie, right? And so then this is where you would tell Ansys, maybe look out for a lot of comedy, maybe look for for a lot of action, maybe a lot of explosions, maybe look for certain actors or actresses, right? And so this is where you would define to Ansys, what types of characteristics do you want to optimize over. Okay. And so the default here, you can see here is minimize. Okay. And so that's going to be our goal, right? And so our goal here is going to be to minimize the amount of material that we're using in the simulation. Okay. Right. And you can and then you can change the amount of the response type, right? And and all the other stuff right here. Okay. Right. And so there's a lot of settings that you can do here, and I'm not going to go too much into detail about this, because it gets a lot, but you can see here that there's a lot you can do, right? But the way that you kind of control the optimization to do certain things, this is where you would do it. Okay. And so by default, whenever you run an optimization, you have a single objective function. Okay. But you can add more too, right? And so if you want to add another objective, you can do that here. So you can just right click add. Okay. And you can choose more things to optimize over. Okay. But for this case, I'm just going to do the one, right? So let me go ahead and delete these. Okay. Because right now we're just doing a very basic optimization where we're optimizing on the amount of material that we're using for our part. Okay. Okay. So any questions on this so far? All right. So last thing we need to set before we set this rolling is the response constraint, okay? Right. And so every optimization algorithm out there has a way to constrain it a little bit, right? And so what that means is, a constraint basically is a way for you to tell the optimization framework to not go so far, okay? Because you'd be surprised, because optimization algorithms they kind of have a mind of their own. So if you don't constrain them, they can do all kinds of really crazy stuff, okay? And so in this particular case, we can place a constraint over how much mass do we want to have remaining after the optimization is complete, okay? And so basically we can control how conservative or how aggressive the optimization is going to go, okay? And so right now we have a response constraint of 50% mass, right? And so what that means is that, you're telling Ansys that after the optimization, I want to retain at least 50% of the current mass, okay? And so don't go too crazy, okay? And so we can change this. And so, let's change it to 75%, okay? And so if we change this to 75%, what we're telling Ansys is that, that we want to retain 75% of the mass, okay? And so Ansys will only be able to delete 25% of the mass, okay? And so what Ansys will do now is it'll look at your model, it'll run its optimization, and it'll find the bottom 25% of this wall bracket that's doing the least amount of work, okay? And so it'll find that bottom 25%, cut it out of the model, and then give you a much more optimized geometry after that, okay? And so you can play with this. And so, today, I'll test this out for different ones so you can see its effect. And so actually, for this particular activity, kind of in its simplicity, this is going to be the parameter that has the biggest impact on our results. Okay. So any questions, on this before we hit solve and we see how this thing works? Okay. All right. So let's go ahead and hit solve. Okay. And so this is going to take a little bit of time. And so optimization is never complete or never never an efficient thing. Okay. But the nice thing about topology optimization is that you can kind of track its process. Okay. Oh, it's no good. Wait. Let me go ahead and hit solve. The files required from the linked analysis are missing for topology optimization solution. Please resolve. Please resolve the analysis in the solution section. What does that mean? Okay. Huh. That's a new error. This is the semester for new Ansys errors that I've never seen before. All right, so maybe let's rerun our solution back in the static structural and then give this another try. Okay. So let's go ahead and do this. Okay. Is anyone else that's following along? Are you guys having the same issue as this? Oh, good. Okay, so some people got it to work. So that's good. Okay, good. Was there something that I missed? Sorry about this, guys. Should have tested this out before I went. Yeah, the results look interesting. That's for sure. Let's see here. Yeah, so it almost looks like someone kind of took a bite right out of your simulation, right? Right out of your model, right? Let me try this one more time. me try loading a previous year, because I think I saved the one from last year too. I think that should work. All right, so for those of you that that got it to work, oh yeah, maybe it wasn't linked properly. Yeah, let me try the one from last year and I'll see. So for those of you who've gotten it to work, go ahead and try modifying the restraint or the constraint, right? And so instead of 75, try lowering it down to 25%, and see how that affects your results. Right? And so I think you'll be surprised at how how that changes your results. All right, here we go. Okay. Yeah, so you can see it's it looks pretty scary. Okay, and so let me go ahead and change this. Right. So let's try 50% now. Okay. Right. And so if you did 75%, for those of you who have done it, it looks like this, right? And so it looks like Cookie Monster kind of took a bite out of your bracket. Okay. But let's actually compare these results right here compared to what we saw from the stress, right? And so we looked at the equivalent stress earlier in our static structural. You can see that these areas of the model here, we're not really doing that much, right? Because we have pretty low structural stress, right? And so if we compare that to the results of the topology optimization, you can see that these are the exact regions where Ansys said, these regions aren't really doing much. They're not really supporting any weight. And so let's just get rid of them, okay? We'll unleash Cookie Monster on them and then we'll get rid of these guys, okay? All right, and so this was a fairly conservative, optimization. And so we still retained 75%. And so let's change this down to 50 and then let's see how that affects our results. Okay? All right, so this looks like it's running. All right. And then while the optimization is running, you can actually click on this topology density tracker right here. And then you can actually see it optimizing in real time. Right. So you can see it's doing some really crazy stuff, right? Okay. Right. And so at first, what it did, what you can see here is that it kind of got rid of everything except for the boundary conditions. And now it's re-adding material to it in order to satisfy our constraint. Okay. Right. And you can check the progress for the optimization down here in the bottom left of the screen. Okay. And so it's actually kind of good that my computer is kind of slow right now, because it's now you can kind of see this optimization take place in real time. Right. And so you can see that the material is kind of slowly being re-added to this to this geometry here. Okay. Still rolling. Okay. And so you can see for this case, we actually don't even get close to the 500 iterations that we had, and so it's only iterating about 16 times. Okay. Right. And so here is here are the results that we have. Okay. So you can see here that we've gotten rid of a lot of the model, right? And so in fact, you can see here that there's one big change, is that Ansys says that instead of having one big bracket right here, why don't you just have two smaller ones, right? Because the loads are only being applied here at the holes, right? And so it's kind of a waste to have kind of one big whole bracket like this for that whole thing. Okay? And so this is that 50%. And so, you know, for 50%, you know, it only retained 50% of the mass. And so that's what I have here. Yeah. And so let's try 25% so that we can kind of see what that looks like. Let's go ahead and hit solve again. Right. Let's go ahead and track this as it goes. Right. And so, you know, if you are doing this activity, you know, what I tell you in the activity is to basically try this out for several different percentages, right? And so we've done 75%, we saw 50%, and then, you know, now we're going to see 25% and what that looks like. Okay. And so another thing I want you guys to try is I want you to try a different loading scenario. Okay. And so, you know, the thing about optimization is that it depends a lot on, you know, how what the boundary conditions are for the simulation. Okay. And so for this, you know, we're only testing one loading scenario where we have, you know, we put the loads here on these parts of the model, and we constrain it here, right? And so, you know, if you change those loads, so, you know, maybe you put the load in a different direction, or maybe instead you put a distributed load on top, right? And so that's going to change the results of your optimization, right? And so, you know, for the activity, if you're going to do it, then you know, you would need to change the loading conditions, right? And then from there you can see, you know, how that's going to affect your optimized geometry. Okay, and so that's you know, another angle that you can take this this activity. Okay. And another thing that you can try, and I know on the activity says this is for graduate credit only, but another thing that you can try is that you can try a different wall bracket as well. Okay. And so here, you know, you have this kind of very simplified one that I kind of just threw together really quickly. But, you know, if you want to try it on a different, you know, wall bracket, you can see how that affects the results for that. Okay. And in fact, you know, if you want to try this for your project, and so, you know, for your final projects, if you have some sense that, you know, maybe I'm using too much material for this, or maybe I can optimize this geometry a bit more, then you can try this on your project and see what you get. Okay. All right, and so here are the results for 25%. Okay, so you can see here that 75% of the model has been stripped away, and we're only left with these guys. Okay. All right, and so I picked this for kind of the last activity because I think, you know, it's kind of fun to look at, but it's also, you know, I think it's a real concern that I think that is asked a lot in engineering is, you know, can we make the same part for less material and have it still do the same thing? Okay. All right, and so the next question I think, you know, people generally ask is, you know, we have these results for this from this optimization, and so what can we actually do with it, right? Because, you know, you're not going to take this part right here and you're not going to take it to the machine shop and you're not going to make a scraggly looking thing like this, right? That's just silly, right? And so, you know, the results of this optimization, you know, don't take it as like word of God, right? And so, you know, don't say that, you know, this is kind of the most optimal geometry, and then, you know, you try to go recreate this, right? That's just not practical, right? And so the way that I see this topology optimization used most in practice is to mostly use this as a guide, right? And so now that you have these results, so you can see here that all this material in the middle here is not needed, right? Now you can go back into your CAD geometry, you know, load this up in SolidWorks or maybe in Design Model or things like that, and then, you know, manually use that and then use this as a guide to say, you know, let's take out this huge middle section of this bracket right here, right? Save ourselves on a ton of material, and then, you know, use these kind of two smaller brackets to accomplish the same thing, right? And so and so in other words, you know, you should use this topology optimization mostly just as a guide, you know, for what you're going to do, you know, with your design, and don't actually do this, right? And so, you know, don't actually, you know, turn this into your supervisor or your manager and say, this is the perfect geometry right here, because it's, you know, it's just one, right? remember, optimization, it doesn't find the perfect solution, but it finds one that's pretty good given the characteristics that you gave it, right? And of course, there's a lot of other factors that go into play when you're designing a part, right? And so, a big factor is, ease of manufacturability, right? And so even though this geometry right here might be optimized in terms of the stress distribution, it's definitely not optimized in terms of, being easy to manufacture, right? And so when you go and use this tool, you kind of have to combine knowledge, and you have to combine factors from a lot of different sources in order for you to get the perfect geometry for your application. Okay. But yeah, don't use this tool straight up and then turn this into your manager or anything like that, because they'll probably look at you weird and think you're crazy, right? Because there's no way that someone's going to manufacture this, right? Okay, so any questions on this? All right, and so that's topology optimization, and so that didn't take the whole time, right? And so let's go ahead and continue back where we left off on thermal stuff, right? Because now that we have the guest lecture planned for next Thursday, I do want to finish up thermal simulations and fluid simulations before then. And so that next Thursday, we can just have it all for the guest speaker, okay? All right, so let's look at heat transfer simulation in Ansys, okay? I think last time where we left off, we just finished talking about, all the different factors that you can include, right? And so, we talked about all the boundary conditions that you can include in internal heat generation, right? And so now let's talk about some of the outputs that you can see, right? Because whenever you're doing Ansys, okay, right, one thing that you always have to specify is, what solution fields that you want to look at, right? And so traditionally for structural simulations, usually the two results that we're most interested in is the total deformation. And so that'll tell us, how much of our model is deforming, right? And so the other thing that we can look at is the equivalent stress, which is, how much structural stress that the part is undergoing, okay? And so for thermal simulations, we have different outputs that we're usually interested in, okay? And so the first output that we usually look at is temperature, okay? And so temperature is pretty straightforward. It's just how hot or cold is our part, right? And so the temperature field is something that you can output from Ansys, and it's something that's very easy to do, okay? Right? And so when you output the temperature distribution, you literally look at kind of a heat map here, right? And so you might look at something that looks like this, where you have areas that are red here, which are at a higher temperature, okay? And then areas that are blue, which are at a cooler temperature, okay? And so kind of the color scheme works really well here, because the red means hot and blue means cold, okay? Right? And so temperature fields are really useful because, first of all, that's probably the first thing that you're looking at when you're thinking of a thermal simulation, because you want to see how hot your part or how cold your part is going to be, okay? And the temperature is usually a good indicator, because that'll tell you whether your part is going to melt or not, right? Because usually if the temperature gets above the melting point of your material, then that's going to melt your part, okay? And so, whenever you do a thermal simulation, temperature is almost always something that you're going to be looking at, okay? And so make sure that you include that as part of the results, okay? All right, and so if you have areas that are melting, then that tells you might need to rethink or redesign your thermal design, okay? And so that's usually the first thing that you look at, okay? All right, and so the next output that we usually look at is heat flux, right? And so temperature is a measure of how much internal energy that your part is holding at a given place, okay? Heat flux is a measure of how much heat that the part is giving off, okay? Right? And so this essentially shows how much heat is flowing in your system, okay? Right? And so remember, when we think of heat, usually we think of energy transfer, right? And so, the heat flux boundary condition, or the heat flux output here, tells you how much heat is basically flowing into or out of your system, okay? Right? And so this can be really important. And so this could be an important output that you're looking at, because maybe you're designing a part that's trying to transfer heat efficiently from one region to another, right? And so one example for this is, let's say that you're designing a heat exchanger, right? Maybe you're designing like a radiator for a car, or maybe you're designing like an HVAC system or air conditioning for a house. Okay. And in those situations, you want to maximize the amount of heat transfer that goes to and from that system, right? And so let's say, for a heat exchanger, you want to maximize the amount of heat that's being exchanged between your two fluids, right? And that's going to be a well-designed heat exchanger, right? And so, heat flux is actually a vector quantity, right? Because heat, or energy transfer, not only has a magnitude, but it also has a direction in which it's going, right? And so you can view the heat flux in all three of the Cartesian directions. So that's X, Y, and Z, okay? And you can also view the total heat flux, which kind of shows you kind of the magnitude of the heat flux, in a, in a certain location, okay? Okay, so any questions on that before we jump into an example simulation? Okay, all right, so let me go ahead and close this, right? And I think I have the thermal Ansys project already done. Let me see here, fluid test, anisotropic, activity 5. Oh, I don't. Okay, so we're gonna have to do this from scratch. So that's totally fine. So let's go ahead and create a new project. Okay, all right. And so we have a blank Ansys Workbench here. Okay, and then instead of a static structure, which is what we normally do, since we want to do a thermal simulation, we're going to go ahead and click and drag steady state thermal onto this location right here. Okay. All right, and so let's go ahead and create our geometry. Okay, and so since it's a for this example, we're just going to do a simulation over a cylindrical fin. Okay, and so I'm going to go ahead and create this cylindrical fin within design model. Okay, and so from this example, you can see here that it has a length of 100 centimeters and it has a diameter of 5, right? And the cross-sectional shape is just simply a circle. Okay. Right, and then all the other quantities, we'll deal with later. All right, so first thing, let's go ahead and create our geometry, okay? And so just like we usually do, we're going to create a sketch, right? Let me change my units to millimeter, or centimeters, sorry. Okay, let's go ahead and draw a circle. Right, let me go ahead and dimension this. Okay, and we want a diameter of 5 centimeters, okay? And then from here, let's go ahead and extrude this. Right. Click extrude, we're gonna click the sketch, and we're gonna extrude this for 100 centimeters, okay? We're gonna hit generate, right? And here is our fin, right? And so we have a nice long cylindrical fin. All right, so let's go ahead and close out of this and jump into Ansys Mechanical again, right? And so even though we're running a thermal simulation, the thermal simulations are actually run within the same program, okay? And so the setup for the mesh and everything it should all be very familiar to you. Okay. And so here is our fin, okay? And we have the cylinder looks like this. And so first thing, let's go ahead and insert our mesh, right? And so for sizing, let's go ahead and select this whole thing. Right? Did I say what size that I used? I did not, right? And so let's go ahead and use a mesh size of, let's say, 1 centimeter. 1 centimeter, okay? And then let's go ahead and add our method object, okay? And remember, we're running a thermal simulation here, and so we don't have to do quadratic elements anymore, right? And so let's go ahead and let it choose the shape, okay? And so let's go ahead and set this to have a linear finite element, okay? All right, so let's go ahead and generate our mesh. Okay. Oh, it actually chose hexahedral elements here. I think I chose the elements to be small enough such that a hexahedral element will work fine. Right? So that's okay. That's fine. Right? And so we can check the number of elements. And you can see here that we have 3,366 elements in this mesh. Right? Okay. All right. And so now let's go back to the example here. Okay. And now our next step is going to be to apply boundary conditions. Okay. All right. And so our boundary conditions are the following. And so on one end of the fin here, we have a fixed temperature of 100 degrees C. Okay. And then on the right side of the fin, which is indicated by this kind of, this shaded area right here, we have a perfectly insulated condition, right? And so let's start with those. Boundary conditions. All right, and so to specify a fixed temperature, we're going to go ahead and right-click Steady State Thermal. We're going to go to Insert, and then we're going to insert a temperature boundary condition. Okay. All right, and so make sure we're on face selecting mode. Okay. This cylinder is symmetric, and so it really doesn't matter which side that we put this on. Okay, but let's put this on the left side here. Okay, and so we're going to go ahead and apply it. And so now we have a temperature boundary condition. But right now the temperature is being set to 22 degrees C, which is what we don't want, and so we want this to be set to be 100 degrees C. Okay. Okay, and so that's the fixed temperature on one side, and let's go ahead and insulate the other one. And so remember, an insulated boundary condition basically states that the amount of heat flow or heat flux through that surface is going to be 0. Okay. And so let's go ahead and right-click Steady State Thermal. Go ahead and go to Insert. Okay. And you can see here that we have a special boundary condition here for perfectly insulated. Okay. And so let's go ahead and click this. Okay. And then we're going to apply it on this surface right here. Okay. All right. And so this tells us that, on this side of the fin, then we have no heat flow that goes off that. Okay. All right. So any questions on this so far? Good question. And so there's a question of, what's the difference between heat flux and heat flow? And so, they're very similar. Boundary conditions. And so they both, want to express a certain amount of energy coming across. Right? But heat flow, you can see, is given in units of watts. Right? So that's what this boundary condition here. Oh, why do I have two? That's weird. Oh, that's my insulated. Right? Heat flux, on the other hand, has different units. Right? And so if you go to heat flux, you can see the units for that is watts per centimeter squared. Right? And so it's like an energy transfer over an area. Right? And so you can almost think of this as kind of the difference in between a force and a pressure. Right? And so a force has a units of newtons. Right? Whereas pressure has units of newtons over area. Right? And so that's kind of the same difference between heat flux and heat flow. So heat flow, that's kind of like your base kind of amount of energy transfer, and so that has units of watts. Okay, but if you want to distribute that energy transfer over an area, just like similarly, pressure is like a force distributed over an area. That's when you would choose heat flux. Yeah. Mm-hmm. Yeah, good question. It's they get confused for each other a lot because their names are very similar. Okay, and so those are the end boundary conditions, right? And so now we need to apply boundary conditions on the lateral surface. Right? All right, and so if we look at the project specs, you can see here that we are going to apply a convection boundary condition. Okay, and so as do most fins, right? And so if you think about a fin is a type of structure, a thermal structure that's used to kind of offload heat. And so by design, they're kind of like these, these structures that kind of jut out, and so that so that they can be cooled, either by a fluid or by radiation. Okay, and so we're going to apply a convection boundary condition on the lateral surface of this fin. Okay, and so I right-click Steady State Thermal, and I click Insert, and I click Convection here. Okay, and then for this convection, let's go ahead and select the outer surface of this cylinder here. Okay. And then from here, we have to specify two quantities. Okay? And so remember, when we talked about convection before, we said that we have to specify both the ambient temperature, right? And so this is basically the temperature of the fluid. And so for this case, we're going to assume room temperature conditions. And so we're going to assume that the ambient temperature is just 25 degrees C, okay? And the other thing we have to specify here is the film coefficient, okay? And remember, the film coefficient is the same thing as our convection coefficient, right? And so if we go back into our, our tutorial here on thermal simulations, right? We can see here that for convection, we have this parameter H, okay? And so here I call it convection coefficient. In Ansys, they call it film coefficient, but they mean the same thing, right? And so remember, what H here represents is how strong the convection heat transfer is going to be, from this structure, okay? And remember, H here depends on a lot of different things, and so it depends mostly on the fluid mechanics of the fluid that's flowing over here, okay? And most of the times, this H, this film coefficient is usually very difficult to estimate, right? And so you're either going to need you're going to need knowledge from your 407 class, or you're probably going to need knowledge from another flow simulation that you might run in Ansys, right? And so if you're running a convection boundary condition, specifying this film coefficient here is usually the most difficult part, okay? And so unfortunately, we don't have time to really go over a lot of methods for doing this. And actually, I think it would be really cool to run a fluid simulation to do that. But just for the sake of this tutorial here, I'm just going to set this to be some nominal value of 5e minus 5. Okay, and so that's 0.00005 watts per centimeter squared. Okay, right. And so that's a pretty small convection coefficient. And so what we say is that maybe we don't have that much convection going on in this case. Okay. So any questions on this? Okay. All right. And so that's the convection boundary condition. And so now let's do the radiation boundary condition. Okay. All right. And so let's go ahead and right-click steady state thermal and go to radiation. Okay. And just like before, we have to specify a surface on which we want to apply the radiation boundary condition. Okay. And so let's go ahead and select this surface out here. Go ahead and hit apply. Okay. And we have to specify two things here as well, right? And so first thing we have to specify is the ambient temperature. Okay. And so we're going to set the ambient temperature equal to 25. And so the same thing as the convection. Okay. And the other thing we have to specify here is the emissivity. Okay. And remember, emissivity is this parameter epsilon here. Okay. And so the emissivity is a property of the surface, and that tells you how well that surface is at radiating heat. Okay. And so usually it's some value between 0 and 1. Okay. And so for this case, we're going to assume a emissivity of 0.3. Okay. But again, this would be something that you would look up from a table, right? And so let's say that we know, in this case we kept the default, and so the material for this fin here is structural steel, right? And so normally what you would do is you would search up on the internet and say, emissivity or radiation properties for structural steel, okay? And then it'll give you a number for the emissivity, and you would just simply plug that in here, okay? All right. And so that's it. And so that's all you have to set for the radiation boundary conditions here, okay? Because all we're doing is we're saying that the heat from this is going to be radiating out to the environment. Okay. Right. And so that's all the boundary conditions. Okay. And you'll notice here that we applied two different boundary conditions to the same surface, right? And so we've never done this before. And so usually, for our structural cases, we only apply one boundary condition per surface, right? But in thermal, oftentimes you have several different types of heat transfer going on at the same time, at a certain surface, right? And so one way that you can, that you can account for this is by, applying a different boundary condition, different boundary conditions on the same surface, right? And that's okay, right? And so you can apply, all these different boundary conditions on the same surface, right? Because most of the times, like, you are going to have both convection and radiation going on. And so you need to make sure that your simulation is going to account for that. Okay. All right, and so that's the convection and radiation boundary conditions. And so let's go ahead and set our outputs. Okay, so I'm going to set one output for temperature. I'm going to do another output for total heat flux, right? Just like we mentioned before. Right? And let's go ahead and hit solve. Okay, and you can see here are our results. Okay, and so you can see here that we have a temperature, a maximum temperature of 100 here at the left-hand side of the fin. Okay, and that rapidly decreases down to 47.42 here at the other end of the fin. Okay, and so you can see here that we have kind of a rapid decrease of temperature, from one side to the other, right? And that usually makes a lot of sense. Okay? And if we look at the heat flux, you can see that we have a similar distribution. Okay, and we have a maximum heat flux here at the left side of the fin where the temperature is the highest. Okay? And intuitively, that makes a lot of sense because the heat transfer, depends on the temperature difference. Okay, and so the temperature difference in this case being the difference in temperature between the fin and the outside conditions, right? And so the outside conditions here have a temperature of, 25 degrees C, right? And so the fact that the left side of the fin here has a temperature of 100 means that we're going to get a much higher, amount of heat flux here from the left-hand side than we do from the right. Okay. And so this is the, these are the temperature and the heat flux results. Okay. And just like we usually do, we can change some parameters here, right? And so let's change this convection coefficient. Okay. And so let's make this a little bit higher. So let me take away 1, 0. And so now we're at 5 times 10 to the minus 4, right? And so what you should see here is that there's the temperature should drop off a lot more. Okay. And you can see that it does, right? And so you can see now the minimum temperature, instead of being 47, is down to 31. Okay. And the reason for that is, we've increased the amount of convection by increasing that convection coefficient. Okay. Right. And so, you can play around with the numbers on this and see, how that affects your results. Okay. So let me go ahead and take 1 more 0 off, increase the convection by another factor of 10. Okay. Right. And so you can see here that, our temperature drops even more. Okay. So any final questions on this? Okay. All right, so that's the introduction to thermal simulations. And so, I know we kind of just scratched the surface and we just did kind of a simple case, but I wanted to at least let you know, that the capability is out there, and at least how to set it up in principle. Okay. All right. So next Tuesday, we're gonna go over how to do fluid mechanics simulations in Ansys, and then next Thursday, I'm gonna try to get our guest speaker. Right. All right. And so that's it for me. And so thank you guys for tuning in as usual. Hope you guys have a great weekend, and I'll see you guys next week.
Okay.
Thanks, guys. Thanks, guys.